organisms, this will result from either inexperienced observers, such as human error, or field terrain that makes it impossible to see every single animal, such as fish, all living underwater. All right, so now let's move on to fisheries data. There are two types of fisheries data: fisheries-dependent data and fisheries-independent data. Let's go over fisheries data first. So fisheries-dependent data comes from the commercial fishing industry. Its big advantage is that it is much less expensive to collect than fisheries-independent data. It's collected from either observers, like the ones employed by NOAA, or from log books, or it can be some combination thereof. You can see this is a fishing boat right here. Again, it's much cheaper, but it has two problems. You can get bad results if you have an effort creep issue, or you can get bad results from hyperstability and hyperdepletion if you're basing your results based on CPUE. Now, fisheries-independent data, which is the focus of this study, it comes from scientific organizations like NOAA or ICES. It's an application of sampling theory because you are just taking a sample of a fish and then extrapolating from it. Its benefit is that it's subject to very strict scientific protocols. Also, it can be modified as conditions change, more data is gathered, more technology is improved, like you get a nicer, better boat to do stuff with. As you can see, this is a NOAA vessel. However, it is much more expensive to collect. I was supposed to have a figure, unfortunately, that was impossible to come by. And of course, governments do have limited resources with which to collect fisheries-independent data, as they have limited resources to do anything. So, since governments have a limited resource, what will be the impact of decreased sampling on the estimates of management quantities of interest? And that is why we use simulations. Okay, so the big challenge that in real life is that we can never know the true underlying dynamics of a population, such as the true spawning stock of biomass of a fishery, and this is going to create uncertainty. You can't know what the truth is, you don't know how biased your model is or how variable your model is. But simulations allow us to actually just specify the truth. And given this new truth, we can simulate a variety of data collection strategies to determine the effects of bias and precision on the estimate results. You can see up here, this top one, the colors didn't come out quite right, but there's a black line, which is the truth, and then a red line, which is our model, and we can use this to see just how biased our model is. On this bottom one here, there's a black line, which is the truth again, and then all these colored lines are our different models, and we can use that to assess how variable our models are. Okay, so now we should talk about how I ran these simulations. And so first we used stock synthesis, which I'm calling the backbone. Stock synthesis, it's a statistical modeling framework used to assess fisheries with a wide variety of life histories from a wide variety of regions. It can be used to assess the impact of various amounts of data on the estimated important stock parameters of interest, such as from those from data-rich fisheries and data-poor fisheries. Previously, it's been used to estimate the impacts of different amounts of biological data on the final stock assessment parameters. It's run using a series of text files, which you can modify to change to collect different amounts of data or estimate different parameters. The problem is these text files are really hard to modify, and it's really hard to do multiple simulations at a time, which is why we use SS3Sim, which I'm calling the machine for our product. SS3Sim is an R package used to run simulations in an easily reproducible, much, much faster manner than SS3. It has an operating model, which is the truth that I talked about earlier, and an estimation model, which is our mock stock system in our made-up fishery, that samples from the operating model with error, specified amounts of it. You can run many hypotheses, scenarios, and iterations, which I'll get into all that what means in a second, at once. Scenarios can be easily modified in RStudio, so there's no need to open up the bulky text files and modify it there. It also has integrated models where it is estimated via penalized maximum likelihood. And so now let's take a look at my scenarios. So my scenarios vary sample size and vary observation error. So the sample size is varied as basically the number of toes collected on a survey. So if you do more toes, you spend more money, cost more. So all the way from 25 toes up to 150 toes. And the observation error was the standard deviation of length and age data collected from surveys, all the way ranging from 0.025 all the way up to 0.15 standard deviation. And now here's a little graphic of how framework works. So I have one hypothesis, which is the sample size and observation error, how variable that changes. I have a set of scenarios, so sample size 25, observation error 0.1, sample size 25, observation error 0.05, all the way down through the 25. And then I have a specified number of iterations. In real life, I have 100, but I only put 2 here because space is a thing. All right, and here's just a little bit of the under the hood on how this works. You can see in blue where it is circled that is where I'm changing the standard deviation for length and age data in my simulations, and in red is where I'm changing my sample sizes. You can also see up top where I have it circled, where it says iterations 1 to 100. That means I'm running it 100 times. And then, 2 days later, these take a long time to do, we get this fun little thing. This is a gigantic data frame in R that has all of our results from our mock stock assessment, including the value of the standard spawning stock biomass and the standard deviation of spawning stock biomass, which those two columns on the far left are really what I care about. So now let's talk about the model setup and how it works. So first, the biological parameters. We based it on a North Sea cod, which is generalized to most species which have a moderate growth rate and a medium lifespan. Growth is assumed to follow a von Bertalanffy curve, which you can see up here, meaning that it will eventually slow with age. Model is single sex, and it grows constantly, though it does slow with age. And fecundity was assumed to be a function of age and follows a Barrett and Holt relationship, which you can see here, and meaning it eventually plateaus. All right, so in our fishery, the fisheries existed for 100 years. We are only looking backwards. We are not looking forwards. We're not projecting forward on this. Fishing began in year 25, or year 26 rather. We used the first 25 years as a burn-in period, just to get our model to settle down and start working correctly. Surveys were conducted first in year 62, which simulates how it works usually in real life, where you don't manage a fishery at all for the first however many years of its lifespan. Some stuff goes wrong, you realize, oh no, we need to do some science and get it to work. And then you do some science and start working. And then stock census began in year 26, same year as the fishery. This is a fun little graphic that just shows what was happening here. So you have the fishery running from 26 to 100, and then you have the surveys running from 62 to 100. All right, so now let's talk about the selectivity. Selectivity is just the portion of fish at each size that are caught. So if fish at a certain size have a 95% selectivity, 95% of fish at that size are going to be captured. Ours only utilize length. Sometimes we use age, but we just use length. And you can see these curves here. The line toward the back is for the fishery, and the one toward the front, the more solid one, is for the survey. And the middle line there is just the 50% selectivity, so 50% fish that size are caught. The survey has a higher selectivity in that more fish at that size are caught, because in a fishery you would never catch really small fish because you couldn't sell it, but in a survey you would because it's biological data that's important. And you can see the parameters there. Okay, so let's talk about how I dealt with error in these models. So observation error was varied by varying the standard deviations of the length and age data, like I showed earlier in the data frame. Process error was done by fixing the recruitment deviations, so just the deviation on how much recruitment you have in the fishery, and then those were fixed between the scenarios, so like the 25 sample size, 50 sample size going on, but varying between iterations in each scenario. Okay, so let's talk about the parameters that I was estimating. So I looked at this earlier, but what I'm really looking at is the spawning stock biomass and the coefficient of variation of said biomass and the number of times it falls within the confidence interval. So spawning stock biomass was estimated in year 100 of the fishery, or the last year of it. And we do this just so we can make projections about the future, because we know what happened last week and predict in the future. This is defined as the combined biomass of reproductively mature females. It's an important quantity for managers because you use it to set reference points, either limit points where we have to close the fishery, or target points where we know we're right on track. The coefficient of variation is the next thing we looked at. And it's a measure of variance. I should mention also too, spawning stock biomass is mostly a measure of bias, and coefficient of variation is a metric of variance. It's the mean divided by the standard deviation. It allows us to compare standard deviations with different means. A high coefficient of variation is bad. It indicates a high variance. And then the final thing we looked at for a bit was the number of times that our estimated value fell within a confidence interval. So we ran it 100 times. Ideally, it should fall within the confidence interval 90 of those times. It didn't exactly work, but it's fine. I'll explain in a moment. Basically, it's used to judge a model performance. Because those recruitment deviations I talked about a moment ago were log normally distributed, our estimated quantities should be normally distributed. And yeah, if that's not working, then we have some problems with our error. Okay, so finally, let's get into our results. So you can see that we have, okay, so I should probably sign this right. So this is the spawning stock biomass from every iteration in these box and whisker plots, faceted by the observation error, and then moving on the x-axis in our sample size. You can see that we have a higher interquartile range, which means a little bit more variable when we have a low sample size or a higher observation error, which is what you would expect. You can also see that the vast majority of variation in these is being driven by the sample size. You can see when you move in these different panes that it doesn't change all that much, but you can see that it changes quite a bit when you move through the sample size. You can also see that this red line here is the truth, like it's the truth that we specified in the operating model. And you can see all boxes encompass the truth, which is good. It means there's low bias. Okay, moving on to the coefficient of variation. So we have a roughly similar trend. It's the same setup, faceted by observation error and then sample size on the x-axis. Similar to the point where a lot of it's being driven by the sample size. However, as you can see, there's a little bit more being driven by observation error, especially when you move from 0.5 to 0.1. There's a nice jump. And then when you move down from 0.1 to 0.125, there's a jump again, and then a jump up to 1.5. The other thing that you can see is that kind of the hockey stick. So you can see that you get decreasingly little, you get lower and lower coefficient of variation as you get greater observation error, or as you get a greater sample size, but the gain you get in decreased coefficient of variation starts to decline. So you get a nice gain from like 50 to 25 to 50 and then 50 to 100, but like it gets lower at the end. All right, moving on to our confidence intervals. So as I mentioned earlier, this is kind of a model performance metric. So we got this to land within the confidence interval between 83 and 95 times. It should be ideally 90, but it didn't quite work that way. And that's just because our estimated quantities aren't exactly normally distributed. They're close to normally distributed, but they're not exactly. It's still acceptable that it happened 83 to 95 times. You also have a higher number of times in the confidence interval when you have a high observation error. So you can see in the 0.125 and the 0.15 panes, that's much higher than the 0.025. And that's just because those confidence intervals are bigger. And then we also calculated this thing called depletion, which is both a model performance metric and also a fisheries metric. That is just the spawning stock biomass in the final year of the fishery, which is the year 100, divided by the spawning stock biomass of the fishery during the first year of fishing, which was year 26. It reflects how much it's been exploited the stock has. You want a high value for this because it means you haven't exploited as much of your fishery and there's more left to take from. And then you can see that basically when you have a lower value depletion at the low sample size, so if you move all these to 25, and then high observation error up in the top corner, that it's lower, and then if you go all the way to the opposite corner with a high sample size, low observation error, it's much higher. This kind of just tracks with everything we know about depletion thus far. Okay, so what are some key takeaways from the study? So we have a larger impact from sample size than from observation error on spawning stock biomass. There's a smaller decrease in variance as sample size increases on the coefficient of variation. So it might not be worth it to sample much more than after n equals 100 because you just don't get a good gain after that if you look at most of the coefficient of variation. The true sample size was seen in all combinations of sample size and observation error, which means we have a low bias and everything. Estimated value for the spawning stock biomass 100 fell within the confidence intervals a reasonable amount of time, which is good. We have good model performance, which is nice because these weren't especially complex models. And a high observation error and a low sample size means the fishery will be depleted more, which tracks with everything we know. Okay, so future directions. So us personally, we are going to run the same setup, but instead of testing observation error and sample size, we're going to test the number of years that you do a survey and the sample size. So doing it every 2 years, 5 years, 10 years. That'll be in the final report. It's not in this. As for why, I refer you back to 2 days later. We want to fully analyze our relative errors because those still need to get sorted out. In the future, for other people, these last 3, should test a broader range of observation errors, maybe all the way up to 0.5 we talked about. We want to look at some other life histories other than cod, some maybe sardines who have a short lifespan and a fast growth, or rockfish which have a short lifespan, a long lifespan and a slow growth. We want to maybe make some parameters time varying because all of ours, time for selectivity and whatnot, were just fixed and stay the same for a whole study. And also we may want to test multiple growth functions. And that's that. Thank you once again to Andre and Nico for all your help, and there. Questions, comments, concerns?
Any questions? All right, thank you. Our next speaker is Baxter Gibbons, and he's been working with Dr. Hauser, looking at stranded sea turtles in South Africa.
Hi, I'm Baxter, like you said, and I've been using mitochondrial DNA